Hi, welcome to the Signal Path. In this episode, I have another product repair for you guys. This is an Agilent MXA signal analyzer N9020A. This one is a 20 Hz to 8.4 gigahertz unit. This is the MXA, fairly valuable instrument, and this particular one is equipped with real-time at 40 megahertz analysis band with a whole bunch of other options in it. Unfortunately, it doesn't have the IQ input option. It doesn't have the mixer input option, but nonetheless, it's a very nice instrument, even though it doesn't go very high in frequency. So we'd like to fix it and recover its functionality. Now, it does have a problem. I'm going to turn it on and show you what the problem is. It does run Windows XP, and so it boots up, and so the problem is actually on the RF side. So it should be interesting to try and repair it. Let's go turn it on and see what happens. Alright, the instrument has booted and unfortunately it doesn't even sweep. The reason is because it has an LO unlock condition, and the condition is a severe error such that the instrument cannot do any of its alignment, cannot do any of its startup requirements, and so you see no sweep at all. So we're going to have to check and see what's wrong with it and where the LO failure has happened. This is fairly vague, but we can look at the block diagram of the unit. I think I've gone through the block diagram before, but I particularly chose this instrument because it has an LO unlock condition, and I don't think we've ever fixed an MXA with an LO unlock condition. We fixed one that had an attenuator broken and it had an alignment problem and some other kind of issue. So this allows us now to explore the LO architecture of this instrument and see if we can repair it. Until it's repaired, we won't be able to do any measurements. So let's go ahead and take a look at the block diagram of this instrument and see how it works. Now, in one of my previous videos, I did an extensive close look of the RF block diagram, and the reason for that is because we had an instrument that had several problems. The RF attenuator front-end switch was not working, so it wasn't doing its alignment correctly, and then we had a bad low-band, high-band switch in the front end, which was preventing the instrument from operating correctly at some frequency range. At the same time as doing this repair, I also described exactly how the different mixers in this entire architecture work, how does the instrument handle different frequencies, and what are the differences between the mixers in terms of what kind of LO goes to what point. So we did a full analysis of this, but at the time, we didn't take a look at the LO because the LO was working, so there was no reason to do some analysis on that one. But now our LO is broken, so we get an opportunity to take a look at that. So if you follow this, by the way, you make sure you go and watch the other video, the other repair of the MXA I have on the channel, because that will then give you an extensive overview of the RF part. But here it is. This is our LO section. You can see there are two main boards involved. There is a board called the A16 reference and a board that's called the A14 LO Synthesizer. Either of these two boards could yield the result that we are seeing, basically an LO unlock condition. We just don't know which one it is. And these boards are quite different from each other and perform different functions. So let's go ahead and zoom on one of these. Probably the first one is a good one to start with. And we can take a look and see what's going on. Now, if you look carefully, you can see that this A16 reference board has a ton of outputs. And the reason it has a ton of outputs all over here is because all of these outputs go into everywhere in the instrument. All the different IF conversions, analog to digital conversions, all the different signal generation and synchronization of memory and storage and display, everything is basically derived from all of these different synthesized signals coming out. That's why you can see them, they go into different sections. If this A16 reference is broken, or even part of it is broken, it's going to cause chaos in the entire instrument, and it'll be very hard to track. But nonetheless, we can still analyze this and find out which points we need to take a look at and see if we can find the error. So we have a 10 megahertz reference. This is most likely going to be an oven-controlled crystal oscillator, and that is the core of the entire instrument for the reference. Everything's locked to this 10 megahertz and the frequency accuracy of this 10 megahertz. You can also have an external 1 to 30 megahertz filter in the front, so that's a 10 megahertz input as well, right in the middle of the filter. And there is a time-based steering which allows this instrument to switch between internal and external LO and 10 megahertz reference coming in, so that you can synchronize instruments with respect to each other. This is a really common thing. And then we can see what happens to that. There's a 100 megahertz VCO in here. This 100 megahertz VCO, the phase frequency detector, directly connected to the 10 megahertz output, and therefore we are locking a 100 megahertz VCO to the internal 10 megahertz reference. And then this 100 megahertz goes through a ton of different things. It goes through multiplication by 3, goes through division by 2, it goes division by 5 again, and you can see all the different frequencies that are generated as a consequence of that going to different places, like the calibration, the motherboard, and so on. But we're not interested in this. We're interested in whatever that is going to generate the first LO, because that's where the LO unlock condition is. So we have to follow a different path. Not that these are not important, but this is not what we're looking for. So 100 megahertz over here is multiplied by 3. So now we have a 300 megahertz filter. That makes sense. Goes through an amplifier over here. At the same time, there's an ALC here for leveling the 300 megahertz third LO. You can see how important it is for these LOs to all be coherent to the same reference, because this is a super heterodyne architecture, so all the LOs have to be locked to each other. It probably has a sliding IF architecture like many of the other instruments that we've looked at. So now the output of that comes back over here, and then it gets doubled again. So now we're at 600 megahertz, then it's quadrupled again, 2400 megahertz, doubled again, 4800 megahertz. So now we have a 4800 megahertz signal. It's again leveled one more time with this ALC at this point. Goes into a phase frequency detector again, amplified with the VGA, and then there is a DRO in here, right over here. So this dielectric resonant oscillator is the core frequency generator for the LO portion. It generates a 4800 megahertz signal. This 4.8 gigahertz signal and this 4.8 gigahertz signal are in a PLL configuration so that the DRO's frequency is fine-tuned to match the 4.8 gigahertz signal here, which is ultimately itself depends on the 10 megahertz. But you may ask, why would I put a DRO in here if I already have a 4.8 gigahertz signal? Why do I lock one VCO at exactly the same frequency to another one? The reason is because the DRO is going to be significantly cleaner. So the loop bandwidth of this PLL is tiny, and it's only intended to bring the frequency of the DRO at the 4.8 gigahertz. All these frequencies that are output over here are either much lower, so the phase noise is better, or that they're not so critical in phase noise. Only the data converter part would be critical. So that makes sense. So far so good. And we're gonna have an amplifier and another ALC over here. This thing is full of ALCs. And then we have a few amplifiers that simultaneously split this signal so it can go into multiple places. And we're going to follow the one that goes to the second stage. There it is. This is a first LO reference, and that's pretty important. The first LO reference, of course, is going to go into the LO board, and that's the one we need to follow. So this makes things quite a bit easier, because if you look, that means that the LO synthesizer board, which follows that, is super simple in terms of its inputs and outputs. It only has a 4.8 gigahertz input, and it has a frequency that goes out, which is variable. Now, in order to achieve a variable frequency, you can see very clearly here the range of the frequencies that this LO synthesizer board produces is between 3.8 to 8.7 gigahertz. And it accomplishes this with its own fractional N controller, but based on the 4.8 gigahertz reference. Having such a high reference frequency coming from here at 4.8 gigahertz allows you to produce a really, really good, clean first LO signal that sweeps with the instrument. So this frequency here is fixed, making things really easy when we want to analyze it. If 4.8 gigahertz is not there, or if it's not exactly 4.8 gigahertz, then we know the problem is on this side, and therefore we can forget about the LO synthesizer. But if the 4.8 gigahertz signal is present, then the problem is going to be in the LO synthesizer board. And let's see what happens to that. The 4.8 gigahertz signal comes over here, goes into this fractional N controller, and this fractional N controller is fed from here at the same time. Now, what I'm concerned with is that this fractional N controller is heavily simplified. Whatever it is, but they're definitely not showing its block diagram. There's a lot more going on here than, of course, just this little block here. So let's see what happens. So we have a VCO again, and this VCO is between 571 megahertz to 1.154 gigahertz. So this VCO is fairly low frequency, and we are locking this VCO to the 4.8 gigahertz. So obviously we don't take the output of the VCO, we're going to have to take it after some multiplication. You can see it's amplified, multiplied by 2, then it goes back here. So now that it's multiplied by 2, its frequency is now double, so 1.1 gigahertz to 2.3 gigahertz. And then that signal comes all the way around here, goes into a three-stage, three output switch. That switch is going to be solid state again. It's going to select 3 different bandpass filters, either this one, or this one. And you may ask why again? Well, obviously because they want to get rid of all the harmonics depending on which range of frequency you're operating. This allows you to sweep the VCO and not have some of its harmonics within the band of interest, creating a pure tone. These are all going to be done on the PCB. And amplified again, doubled yet again, and there's an ALC here, and that ALC output is being taken from here, which is interesting itself. We're going to have to take a look at that. And then you're going to have 3 more filters, and the output then finally goes over here, which is fed back. So if you look carefully, you can see that at this node here, right where the mouse is, we could have any frequency between 2.3 gigahertz and 4.6 gigahertz, and that is fed back in the fractional controller. Now the frequency coming out of here is really close to the 4.8 gigahertz, and the fractional controller simply locks the two of them together. This architecture of having a VCO with multipliers afterwards before closing the PLL loop is a really powerful idea, because it allows you to make a VCO at much lower frequency. The disadvantage is, of course, phase noise, because you're multiplying it up passively, essentially. No retiming involved, I mean. So there it is, and then after that it gets doubled yet again, and then we have another 3 switches. You can see 3 different selections, and then finally the output. So the output at 3.8 to 8.7 gigahertz is going to be the range of frequencies this instrument is going to need in order to perform all of its functions. Keep in mind that this frequency actually does not go higher than this, even in the 26.5 gigahertz version of this instrument, because we're going to do harmonic down conversion, which I've described in detail in the other video. So there it is. So very simple. In reality, we only have to look at 2 points to find out which of these boards are broken. That doesn't happen very often where you have such a simple diagnosis. So we look over here, and you can see we expect this frequency range in this power, and we look over here because we expect only a fixed frequency. And if you look down here, there's a table which is nicely drawn over here. You can see that this table tells you what frequency you should expect to come out of this block depending on where the center frequency of the instrument is set. And if you look over here, between 0 to 3.6 gigahertz, the LO synthesizer output is going to be the tuned frequency, whatever you set it to, plus 5.1225 gigahertz. It has a huge offset in frequency because the low frequencies are up converted, and that's the reason. But as soon as you go between 3.6 to 8.4 gigahertz, the LO synthesizer output is going to be the tuned frequency plus 322.5 megahertz, which is our first IF frequency. So it's all really clear. And at higher frequencies, the division ratios begin to kick in because now you have multiplication due to the harmonic conversion. So it all works out. Now we don't really have to worry about these bottom portion here because this instrument stops at 8.4 gigahertz. It doesn't have all the upper frequency down converters anyway. So it makes it really easy for us to find out what is the frequency you expect to come out of the A14 LO synthesizer. So now we can go back, take the instrument apart, and do 2 measurements, one over here and one over here, and we can already find out which of these 2 is broken. By the way, this is all, I'm already deducing this by just looking at these block diagrams. You don't need any other information. If you look, this service manual is 632 pages. No one's going to have time to read all of that. If you just want to do a quick analysis, you can do so by understanding and figuring out how the block diagram works, which is the purpose of making this video and this portion. And here is the instrument. I've already taken the cover off, and this is the LO synthesizer board right here, and I've done a little bit of extra work on that. Since we were going to take a look and see what's inside of it anyway, I've already taken it out of its enclosure, and this enclosure takes a while to take apart. There's no reason to show you that. It's pretty straightforward, and we've talked about this quite a few times. Now you would never want to run these without the enclosure during normal operation, because not only things are not isolated as they should be, and some of the effect of these ground planes on the walls are taken into account of the design of all the interconnect, all the microwave interconnect. So you definitely want that. And you can also see RF absorbers here built into the chassis to eliminate some kind of a resonance or some kind of a cavity from forming and reflections bouncing back around inside the individual compartments here. So I've already taken this apart, so I'm going to put this aside. But we're going to do this test anyway. And just to remind you, the board that we're interested in testing, first let me actually talk a little bit about this one. So this is the synthesizer board. This is where the 10 megahertz crystal is, this is where the DRO is, and all the different filters and multiplications and PLLs are on there. The output of this is what goes around over here and is fed into this board, and the output of this board is the first LO, which then it goes into the first mixer there. Now, by the way, the clicking noise you're hearing is the MXA booting up and doing self-alignment. So it's either this board that's bad or this board that's bad. Obviously, I'm hoping that it's this board because this is quite a bit more complicated and also a lot more difficult to work on. Although there is one major advantage to this board is that it's all facing up. So you can just probe it and test it, and that would make things a lot simpler. Whereas this one, we are only looking at the sides. So this board over here, here is this block diagram, which is what we talked about, and we went through it extensively, and there is the cat. And so yeah, that's it. This is basically how it is, except it's backwards. So this input coming over here is this input right here, and this output is this one over here. So let's go ahead and turn it on. We can test this guy to make sure that the 4.8 gigahertz signal coming in here is nice and stable with the correct amplitude, and then we can take a look at the output and see which one of these don't work. Okay, the instrument is booting up, and you can see that I have bypassed that connector. It's going to a cable, it's going to the MXA right above, and there are some LEDs over here, which I believe are the PLL lock and unlock LEDs. There you go, it's booting up. It's running Windows XP. And yeah, so let's see what it looks like on the spectrum analyzer. I already see a signal, so it's actually not a bad sign. Looks like there's already something there, but of course we have to look at it close by after this instrument is completely booted. Okay, let's see how good this signal actually is. So we can do a peak search and put it in the center. We can also change the span a little bit. Let's say a span of 50 megahertz. There it is. Looks pretty good, I would say. And then yeah, look at that. That is a 4.8 gigahertz signal, and it is very stable. It's not moving around. This is what you would expect to get. So this already tells us a really important piece of information, that the issue is not from the first synthesizer board, and it's most likely from the LO board. And the amplitude is about 2.8 dBm, which again is correct. Should be a couple of dBm. There's some losses in the interconnect that I have here. But I think this is a pretty good sign that we don't have to worry, therefore, about the first board. We basically can assume that this is functional, since the only part of it that enters in this board is this one. And you can see both of these LEDs are now on. That definitely means that this is unlocked, and this is unlocked, of course, because this is not even connected. So this would have to be this way. Well, let's take this out and examine it closely, and we can go over several design aspects of it, so we can find out what type of measurements we need to do here to debug it further. And here is the board, and of course, as always, the Keysight engineers don't spare any expense, and things are often really complicated with a lot of resources thrown at some other problems. So here they want to make a very clean synthesizer. So let's see what they've done. We have our 4.8 gigahertz reference coming in, derived from a DRO, so it's very clean. It's got some amplification stage in it, and then it goes into a mystery chip, which is on the other side of the board. So which means that this is where the input prescaler is handled. So the reference has to get divided down. You don't want to work with a 4.8 gigahertz reference in a PLL. So there's some programmable divider, and that's most likely what that mystery chip is. So I actually looked into it, and I'm going to show you what I think it is and how it looks like on the inside. But you won't be able to find a data sheet of it because it's a part designed for Keysight by ON Semiconductor. So that's the input reference handling. Now the output of that programmable divider then goes into one of these two FPGAs. So they have two full FPGAs on this board. They are being used for fractional end controllers, as well as all the glue logic required for everything else here. So that's just pretty complicated. Having an FPGA to do your fractional end synthesizer is convenient, because it means you can program it and change its parameters, but at the same time it's quite an expensive way of doing it. So then from the other side we have the output, and you can see at the very end there is an amplifier block here. This is so that it can boost the output all the way up to about 14 dBm. So this is an Agilent branded part, probably not even silicon, maybe 3.5 or gas, something that they've designed themselves. And here's another one over here. I believe that's another amplifier. So this is just an amplification stage. Now we also know that there has to be a ton of selectors and so on, and we have to find where those selectors and switches and attenuators and VCO is. There is a block here that's unpopulated. This may have been some kind of DC-DC converter maybe, or some kind of an oscillator. It does have some very large pins here. Not sure what it is, but anyway, it doesn't need it anyway. There are lots of power conditioning and filtering and DC-DC converters you can see over here, and voltage regulators spread around, and you need those for various reasons I've talked about quite a bit. This is a programming port for the FPGAs. So here at the bottom here is our VCO, and you can identify the fact that it's got groups of varactors, which are made of diodes in reverse bias, and there's a single transistor in the middle. So you can tune this, and it has a really wide tuning range of almost a factor of 2, from 500 to a gigahertz. So the output of that is then taken forward. It's got some leveling, it looks like, and then it goes into another identical transistor, this time being used as an amplifier. That's not surprising. You can of course build a VCO from a transistor or an amplifier from it, depending on how you put matching networks around it. And the output of that goes over here and goes through 1, 2, 3 filters here to make sure there's no other harmonics, and then you need to double it. So for doubling it, what they've done is, since the frequency is fairly low, they pass it through a balun, so single-entity differential converter transformer, putting it into a diode, a pair of diodes, and they bias the diodes at the edge of them being turned on, so this large signal coming from this VCO hits those diodes and pushes them in and out of conduction mode, and that's an exponential transfer function, creating a very large harmonic content. They take the second harmonic of that, they amplify it. Now at this point, is where we have our first selector switch. And you can see the selector switch right here. So now we have 3 separate paths for 3 different filters. Now you look at this board and you say, well, where are the filters? Well, they're actually embedded in between the layers. I'm going to try and see if I can get an X-ray of this to show you the filters that are inside between the layers. Often you see these hairpin filters or various bow tie resonant filters and things like that. You see them on the surface of the PCB, but they're actually not on the surface here in between the layers. And that's for various different reasons, for space and for being able to isolate them and so on. And then there are several filters. All of them have to come together eventually, and they come into this selector switch. After this, we have another doubler. That's a Hittite part. And then we have another amplifier. Sorry, this is an attenuator. So doubler, programmable attenuator, into another selector switch, split into 3 again, and they come back into this one. Right over here, we have then 2 paths. One path is fed over here, going through here, all the way through here, through an amplifier stages, and then onto the mystery chip. The same mystery chip that we saw earlier on the other side, or I haven't shown it to you actually. And that's a programmable divider again, going into some output filters to clean it up, and that goes back onto the FPGA. So which means that the path for the signal between the reference going through here and between the VCO going all the way through here and through here and here and all the way back out here is now known. So that's how the loop of the PLL is closed. After that, everything else is open loop. The next multiplication stages and selectors going to the output have nothing to do with the PLL anymore. It means that if something is broken here, this PLL even wouldn't know about it because the feedback is taken before that part. So I hope that you're looking at the block diagram at the same time as I'm talking about this, because I think if I put it on the screen, it will block a lot of the screen. I'll see if I can maybe put it up here. So yeah, so that's basically the architecture. So where do we test? Oh, by the way, here is another section over here. This section seems to basically detect whether there's a lock or an unlock condition. That's why you have the 3 LEDs here. So it means that, and there's also a couple of test points, one here, and one here. And I suspect because these test points are so close to these LEDs, we should be able to use these test points to figure out if the system is locked. And I think these are basically during testing or debugging are used. But look at how close these guys are to the VCO. In fact, if you look at the VCO, you can see that there's a coarse and a fine tune, and both of those come onto this section. So I am hoping that these signals are actually the same as the signals that control the VCO, which would be a huge help because we can measure the signals that control the varactors on the VCO, and we can see if the PLL is doing what it's supposed to do. At the same time, we can monitor the output and see which frequencies it is showing, and that tells us something about the functionality of everything else. There's really hundreds of things you can test here. So I think a good place to start is to connect this to the spectrum analyzer, see what the PLL is producing, connect these guys to the oscilloscope, and see the correlation between the frequency tuning and these, and see if we can debug and reverse engineer it. We might also take some X-rays of this region so we can take a closer look at the VCO as well. So I think these are pretty good places. The other place we can take a look is in order to make sure that this signal which is coming all the way from here back, is this signal present. We can scratch this trace here and attach an active probe to it, so we can monitor the signal going into the divider and seeing if the signal is strong, has the right frequency content, because there are so many doublers in the way, and if anything is dead, we wouldn't know. So I'm inclined to say that we should measure this guy, and this guy as a starting point, and that should tell us a lot of information about how this works. Okay, let's take a look at our setup here. So I've made a couple of changes. First of all, I'm taking the 3 signals I talked about out, and they're going onto the Rohde & Schwarz RTO2064. I'll show you that in just a second. I'm also taking the output of the LO Synthesizer here, and that goes into the Keysight MXA so we can monitor it. The input no longer comes from the instrument itself. I'm providing my own 4.8 GHz signal directly into this connector from another source. It's an Agilent EXG, and that allows me to change the source in power and in frequency. And then PLL, of course, has to follow that so we can monitor and identify what each of these pins actually are. This is a nice way of doing it because we don't rely on the instrument. We control the reference. We can monitor everything and find out which ports of the VCO are FM and which ports are for tuning. So that should be pretty easy. So this is completely out of the picture this way. I should really terminate this, but anyway, it's now left floating. So let me show you what everything is going on here. So here's the Rohde & Schwarz RTO. This is going to monitor the 3 analog voltages, and we can see them right now. They're all constant because the instrument is in 0 span. And interestingly enough, if you look at the instrument over here, you can see that it is locked. So I found out that the instrument is not unlocked across the entire frequency range, but only some of the frequency range. That's going to make things a little bit more difficult. If it never worked, it would be a lot easier to debug, but it means that it only works sometimes, and sometimes it doesn't work. So we have to find out which frequency ranges it is non-operational. And at the top over here, we have, of course, the the MXA. That's going to look at the spectrum. You can see it's a tone there, so that's working. Over here, we have the Keysight EXG. That's going to give us the 4.8 gigahertz reference, and of course, the cat, who's working, looking outside, making sure everything is good. There it is. Okay, so let's go and do some measurements. So from the service manual, we expect what frequencies we are supposed to get out of the instrument. Right now, the instrument under test has a standard frequency of 3.65 gigahertz. So if I do a peak search over here, you can see that we have 3.98 gigahertz, which is correct. That's how much it should be. It's about 312.5 megahertz above the standard frequency we set. So that part of it is working. Let me go ahead and change just a little bit. Let me increase the number of points here from 1,000 to 10,000. There you go, get a little bit few more digits there. And we can do a peak search, and we can do a continuous peak, so we can track the frequency. And 15 dBm of output power is coming up, which is perfect. That's what it should be. So everything is good right now. Everything is locked. All the PLLs are working. Now I'm going to go ahead and increase the frequency, and this should track it. I'm changing the center frequency of the instrument. There you go. You can see it's tracking it quite nicely. Let's go all the way to the first band. Oh, you can see already some little uncomfortable spots are coming in. Yeah, there's some tones for sure. There it is. And this is 4, still working. Yeah, this might be out. Okay, there you go. Now it's not working anymore. Yeah, it's not moving. There it is. It just lost it. So, yep, indeed, you can see that it cannot decide where to keep the frequency. These spurs that are appearing outside of the PLL band are not good. It means it's going in and out of lock. And indeed, the lights on the little board are also turning on. You can see they turn on and off. It's going to come on and off occasionally because it thinks it's locked and it's unlocked. So indeed, there's a problem. And if I look at the Roden Shore screen, you can see that those waveforms are going absolutely crazy because it cannot keep a lock. So let's go back down to a frequency where a lock does happen. Let's go back to 3.65 gigahertz where we know it works. There you go. It should eventually stabilize. There you go. See, it stabilizes because it searches for a while. Eventually it finds. This is a multiple loops at the same time. There are some analog loops, there are some digital loops, but you can see that the voltages have stabilized. So indeed the frequency is locked again. And if I go all the way up here, you can see that it is stable once again where it should be. Well, let's do a couple of experiments. I think what we can do is we can change the reference and apply an FM modulation to the reference to the LO board. And if it is correct, we can identify which voltages of the VCO are intended for FM tuning. So we can go ahead and try that. I'm going to do this, of course, on this instrument right here. So let me go ahead and set that up. Okay, so here's my FM source. You can see that the reference is at 4.8 gigahertz, 6 dBm, and I do have one FM source active. The deviation is 40 megahertz, so which means that this signal is going to go up and down of 40 megahertz in total around the 4.8 gigahertz carrier. And it's a triangular FM modulation with a frequency of 500 millihertz. So it's really, really slow. This allows us to follow that waveform directly from the VCO tuning voltage and making sure we are definitely inside the PLL bandwidth. So that's going to be an interesting thing to try out. So let's go ahead and look at the Roden Shore screen and see if we can capture that. Okay, let's take a look at DRTO2064. By the way, this is a fantastic oscilloscope. I use it quite a bit in the repairs. Hopefully I'll do a full teardown of it soon as well. So this particular one, you can see all the channels are constant. Everything is on a really, really slow scroll. This is 1 second per division. So I'm going to go ahead and turn on the FM modulation and see what happens to these waveforms. So here's the FM modulation, and check it out. There it is. This tells us that on channel 3, we're looking at the FM tuning port of the VCO directly, because you can see the triangular wave that I apply, the system is following that and compensating for it by tuning the VCO such that the PLL remains locked to the reference coming in. If I look at the output frequency of the system, it's going back and forth with exactly the same amount. So you can see that the yellow line over there, even though it changes when we tune the instrument, doesn't really change here, meaning that that must be our digital pre-tune. And there is the green one, I'm not exactly sure what that is, because it seems to be a combination of the digital pre-tune and the FM tune of the VCO. So this tells me a lot of information. It means that the PLL is basically functional. All of its primary components are working. The fact that it doesn't work across all frequencies is a bit of a mystery, but we're going to dig into that and see if we can figure it out. So I'm now fairly comfortable to go ahead and put some active probes directly on the line there and see if I can see any of those higher frequency components inside the PLL, and then we can tune it and see where it starts failing. Okay, here is our active probe connection. You can see this is the node that is fed onto the programmable divider, the chip from ON Semiconductor, and here's the ground. So there you go. We have now a high impedance active probe connection. This thing should have up to about 8 or 9 gigahertz of bandwidth the way it is set up. I'm going to tape this down, and we should be able to hook it up to the scope and actually see the waveform there. And as we sweep the frequency, we can look at the quality of the waveform. Okay, so here's our connection to our active probe over here, and just to remind you, we are measuring this signal right here, right before it goes back. By the way, there's something wrong in this diagram. This switch is in the wrong place. This signal cannot be taken after the switch. It has to be taken before the switch, because otherwise when you switch this path, you simply won't have any feedback. So the diagram is wrong. But anyway, it doesn't matter. We're measuring right here. So we expect the VCO frequency that sweeps from 570 megahertz to 1.1 gigahertz after it's doubled once here and here to be in the ranges of 4 gigahertz or so. So that's what we're looking for. So let's go ahead and measure that. I already have it set up, and we can go ahead and do exactly what we did on the other instrument and see how the waveform looks. So here's our waveform. We're looking at again the same signal, and you can see the FFT of that signal. It looks nice and sharp. This is when the instrument is set to 3.675 gigahertz or so. So that way the frequency is just below 4 gigahertz. So that's correct. I'm going to increase the frequency, and that tone should move up, and you can see it does. And eventually we're going to hit a frequency where the VCO is going to jump back down in frequency, and because the last doubler is enabled. And let's see what that looks like. So we're going right now at 4.15 gigahertz. Keep going. There you go. You can see this VCO switched all the way down here. Some additional tone on the side. Here's a second harmonic. Now the VCO is a fourth of this frequency. So it still works. And I can go up higher and keep going. You can see it's still tracking. The second harmonic is growing a little bit there. And there you go. Right over here is where beginning to be unlocked again. There it is. It's just lost. But it looks like that this path is actually functional. So if I go back down to 3.65, eventually it's going to catch again. And come on, you can do it. There it is. You can see that it found the frequency again. So that part is working. Now it's going to become a little bit more difficult, because I was hoping that there'd be something wrong in the feedback path with one of the switches, but no, the switches are working just fine. So we have to keep digging. So we looked at the signal right here the first time, and that's the input to this ON Semiconductor programmable divider. And let's look at the signal right after it differentially across these two mini circuit filters. After that, there's a mystery Keysight IC over here, which we're going to have to investigate. But let me see if there's anything unusual happening to this output when we cross the threshold of where the PLL stops working. Okay, same test again. Let's look and see what's coming out. Now this is quite a bit different, of course, because this is after our fractional divider, and the behavior of the PLL is now totally different at this point in the circuit, because before the input reference frequency to the fractional divider was not constant. It's going to go across the range of the frequencies you want to achieve. But what comes out of the fractional divider may be constant. In this case it is, and it's sending out a series of pulses, and these pulses have a spectral content that looks like this. That's to be expected, of course. And you can see that we have several dominant tones. Those are going to be the fundamental frequency of these pulses, and we can measure that. We can see that the frequency of those is about 50 megahertz. So the instrument is keeping the pulses at a constant 50 megahertz frequency. Even if I change the center frequency of the instrument, I'm going to keep going up now, you can see there's absolutely no difference. And that's because the fractional divider is keeping this value at a constant. So I'm going to keep increasing. Even when I switch the VCO, it still keeps it at 50 megahertz. But at some point, the instrument begins to fail. And when it starts to fail, you can see what happens. There you go. It's right now starting to not be able to divide anymore. And there it is. Now I can see it's totally confused. But it was fine up until then. So the input-output relationship is still working. So this is still not the problem. Something else must be going wrong. At least I don't think this is the issue. So we have to keep searching. This is going to become more and more complicated. Hopefully we can find out what's wrong with it. So after everything that I described, I went ahead and I connected two wires directly to the opposite sides of the diodes, the varactors in the VCO. So we're basically looking at the coarse tune and the fine tune at the same time. I also have the active probe connected directly to the output of the VCO as well. so we can look and see what the oscilloscope says. So we get kind of what we expect to get. We have the main tone of the oscillator here. You can see that tone right there. It's at about 993 megahertz, and the frequency center of the spectrum analyzer is at 3.65. So if I go ahead and increase that, you can see that the tune voltage up here, the coarse tune is changing and the fine tune is adjusting automatically. There you go, and we can keep increasing that until we reach the edge, and then it will jump back down. And there it is, and now we are back at the very beginning tuning curve of the VCO at 584 megahertz. We can keep doing this again, and then eventually you can see that the tuning voltage continues to go down, as you can see, and eventually we reach a point where, yeah, it's just lost lock. It can't lock anymore, and it's going to jump around in just a second. There you go. So it's getting confused a little bit again, and there it goes. So I'm beginning to think maybe there's something wrong with the varactors on the VCO, and the tuning curves are just all off, because it has to do some alignment and extract some information at the beginning, and maybe it's just not very good. Unfortunately, the alternative is that there's something wrong in this complex network that I showed you earlier. We can explore that as well, but I think I'm going to go ahead and change the varactors on the VCO and even the VCO transistor itself, just to make sure that it's not the varactor, because if the varactors are bad, even if one of them is bad, then we have a totally different tuning slope of the VCO, and that could cause part of the problem. So let's go ahead and try that. So let's take a look at some X-rays that I took off the board, and they look pretty nice. As I mentioned earlier, the filters for the different bands of the LO synthesizer are buried within the PCB layers, and in the X-ray you can clearly see the filters for the different bands. It's sometimes difficult to bury these filters between ground layers because you're so close to each ground from the top and the bottom that now you have all these extra capacitances, and sometimes it's hard to meet the bandwidth, or just hard to create the characteristic impedances you want with this. But at the same time, it gives you a really isolated design, and then all the cavities that are formed by the chassis and the top and the bottom of the board, they don't matter anymore. So there's some advantage to that as well. You can see that indeed they have buried filters in the layers. The other part that's interesting to look at is the VCO core. So let me zoom in here so we can take a look at the VCO. Here it is, and you can see that the VCO has no grounds underneath it. Everywhere that's black is basically nothing. X-rays going right through it. And you can see the tank design, which comprises of these diodes along these curved traces, which are the inductors. So there's an LC on each side, creating the tuned C with the junction of the diode, and of course the L is fixed by traces. At the same time, you can see these little surface mount inductors. By the way, these devices are absolutely tiny, so the fact that you can see the individual wires wrapped around the surface mount component of this size is pretty amazing on this X-ray machine. And we can also see the different traces here for the coarse and the digital tune. So here's the FM tune line, and here is the digital tune line. There it is, the pre-tune and the FM tune. That's what controls the VCO, and you can see they're isolated by the inductors, which are AC blocks, and they allow the inductor to oscillate internally and be completely separated by the signals coming in. This is a normal technique, of course. This is even done in integrated circuits. So going down here is the output of the VCO. All the way up here is all the analog circuits that control the VCO. So I was beginning to suspect that perhaps some of these diodes are bad, and if the diodes are leaky, they can completely change the characteristic and the tuning voltage of the VCO and the KVCO across the band of operation. So that might be one possibility. So I want to change some of these diodes, remove them, measure them, and see if there's any problem with them. I don't think there's anything wrong with the circuitry up here, because it does work, unless again the slope of some op-amp has changed and something is partially damaged but not completely damaged. It's a very difficult thing to find. At the same time, what else did I take a picture of? Let's see, this one is interesting. So here is the mystery IC that I keep talking about. It's a programmable divider. That's this one. So we measured the input to it. I already put the probe here. We saw that it sweeps nicely. I also put the probe at the output of these filters, and we looked at that, and that was the 50 megahertz signal coming out. If you follow that, you can see that it goes through the transformer and it goes in through this IC. Originally, I didn't know what that IC was, but now I do know what it is, because it has another transformer with a signal coming from the other side of the board from an identical IC like this one. That's obviously the reference coming in. That means that this is a phase frequency detector. The output of the phase frequency detector is then brought over here and is given to these op-amps, which are then processed and create a charge pump. So I was wrong when I thought that the entire PLL functions at lower frequencies were handled by the FPGA. They're not. They're actually done using traditional phase frequency detector, charge pump circuitry, and so on. There are D2A converters for the digital tune, but the analog part of the VCO loop is traditional, the way it's always done. So that's interesting to see. Above here is right where the VCO is, so you can clearly see the PLL loop wrapped around it. This is pretty complicated, but I'm going to try and see if playing around with the VCO components would help the operation here. And then let me see, what else did I take? Here's another one. This picture here shows one of the FPGAs right over here. You can see how many pins it has in a BGA array. Here's the same phase frequency detector I was talking about, and this comes over here and all the way out this side, and the VCO is all the way up there. So it looks good. You can imagine it's going to take forever to reverse engineer all of this. I'm not going to do that. Hopefully we can find it without going through all this trouble. But there are the X-rays. Let's go back to the circuit. Well, check out what I scored from eBay. This board up here is a completely loose board that I bought for 50 bucks. It's a board that someone has already salvaged a bunch of components from. You can see the ADC and the DACs are missing from here, and there's a bunch of other components on the other side missing. So this is completely non-functional. But for 50 bucks, you know, you can't go wrong, and I thought maybe we can salvage some parts from it. So what I already did is I made two changes. I took the transistor from up here, which is the same transistor that's in the core of the VCO, and I moved it into the transistor of the VCO of the board that I'm trying to fix. I also measured every single one of the diodes. I took them off, I measured them, and two of them measured a little bit different than the rest. So I replaced them with two from this board. And in fact, I have the two diodes, just so you can get an idea of how tiny they are. These are the two diodes that I replaced from this board. So I basically brought some components from here to here. I also replaced one of the op-amps on the other side, which is the buffer of the ADC that does the coarse tuning as well. I replaced that too. So a few couple of changes, nothing really major. Let's go plug this back in. I'm curious to see what happens. And oh my god, check it out, it sweeps. It no longer has that problem. This is amazing. Now there's some spurious tone here. It could be because it's open. I haven't put it back into its enclosure. Let me see what frequency that is. I hope that it's not because I've caused a different problem. That's a 211 megahertz. 211. I don't even know where that could be from. My microphone is not at 211 megahertz. It's at 500 something. So I'm going to have to put it back completely to make sure this actually goes away. This is not some other weird spurious thing that I just created. But anyway, that's already a huge step forward because this is a full span and doesn't give the LO unlock problem. This is great. Let's see what happens next. And here it is with the unit back together. As you can see, that tone is completely gone, and that was obvious because there's so much stuff happening on that board and bouncing around inside the chassis. So all I've done is just close it up. It's actually still open at the top, but I've put the enclosure around the board. So let's go ahead and put a 1 gigahertz tone into this and see what happens. Here's a 1 gigahertz looking quite nice. Let's do a peak search over here. Indeed, 1 gigahertz looks good. Let's go higher. Let's try 6 gigahertz. And then we can take a look and see if the signal is nice and clean. That also still looks pretty good. Let's change the center frequency here. Let's go to 6 gigahertz. And let's change the span to something like 50 megahertz and lower the resolution bandwidth. Here, check it out. This is very, very nice. Very clean, you can see. Indeed, we are well within the noise, phase noise characteristics. I've already verified that. We can increase bandwidth and reduce the bandwidth. It looks good. We can increase the span. You can see over a wide span, even in 1 gigahertz, very flat, very clean, good display average noise level. It looks good. I think it works now. Now we can also try a couple of its other features. It does have IQ analyzer, and it has a pulse analyzer, WCDMA analyzer. I think I've talked about a lot of these before. It has an LTE option built in it. These are obviously very specialized. If you were working in WCDMA and LTE, that would be useful. The pulse could be interesting for measuring peak performance of power amplifiers, for instance. It does not have the license for the 89601 VSA, but it's installed there anyway, and very basic IQ analyzer. So I have to say, I think this is pretty good. It's a very successful repair, I think, and I'm going to clean it up and put it aside. Again, I want to emphasize the reason I can do this is because of my Patreon supporters. It's impossible to get these kind of instruments actually purchased and repaired if I didn't have the funding support from my Patreon supporters. So I'm really grateful for that. I hope you enjoyed this. I dug really down into the details of how this instrument works and gone through many different kinds of measurements. Let me know in the comment section what you think, and I'll see you next time.